Hi everyone. Thanks for joining today's installment of the WSA seminar series. We're really glad that you can join us today. So today's presentation is scheduled for about 35 to 40 minutes, which will leave us some time for questions at the end. As we go along, please feel free to leave your questions in the chat, or you can hold on to them and ask them during the dedicated question time. Just a quick note, as you would have heard, this webinar is being recorded. The recording will be made available shortly after we conclude, so you can watch it again or share it with colleagues who couldn't attend. For your convenience, all of our previous webinar recordings are also available to view on our WSA's YouTube. I will share a link to the chat. So today we have Ben Strong from Earth Genome and Lindsey Smart from the Nature Conservancy talking to us about the Seagrass Mapping Blueprint. All right, I'll let you guys take it away.
Thank you so much. Thank you also for having us today. We really appreciate it. Today, my colleague Ben and I will introduce the Seagrass Mapping Blueprint project. It's a global effort to make large-scale seagrass mapping feasible. It's a project that's co-led by Earth Genome and the Nature Conservancy in partnership with Florida International University and regional collaborators from across the globe. Despite being critical ecosystems, seagrass conservation and restoration efforts at scale remain limited. While we identified several policy, financial, social, technical barriers to scaling seagrass conservation, we noted that it's hard to think about conservation at scale if we don't have a really great sense of the global extent of an ecosystem like seagrasses, or what condition they are in, or how they're changing over time. So this project really is motivated by the desire to try to overcome some of the technical barriers to seagrass mapping. And with that, one of the goals of this project is to identify and outline some of the solution sets that address some of the existing challenges or barriers to seagrass mapping by convening, collaborating with, and learning from existing seagrass experts and coalitions that have been tackling some of these challenges across the globe for decades. We also noted that while there are some large-scale seagrass mapping efforts out there, accessing the underlying approaches or methodologies that create the maps is still somewhat limited. So another goal of this project is to really develop a scalable seagrass mapping methodology, leveraging innovative AI technologies in ways that are transparent and open so that they can be taken up and adapted in other geographies freely in the future. Finally, a goal is that we want to really lay the foundation for monitoring seagrass ecosystems through time in an effort to tackle one of those challenges in scaling seagrass conservation and restoration efforts. So the project is largely framed around these two pillars. One, or the first, is that science pillar, which is the development of that scalable seagrass mapping methodology that is open and transparent, that leverages remote sensing AI foundation models, and that is regionally fine-tuned to address some of the unique conditions in certain geographies. We also are creating and publishing maps of seagrass extent, change, threats, and in one of the locations, carbon stocks for these 4 pilot geographies that we are starting to test the methodologies in. The second pillar is this collaboration pillar. The hope is that we are co-developing all of the above science from project initiation by building on existing coalitions of seagrass and blue carbon experts and advocates so that we can ensure relevance and scalability and uptake through time. The deliverables for this project are a digital repository that hosts that open and transparent methodology and model, a dedicated public-facing website, the data, the tools, and the visualizations of the maps in the 4 pilot geographies that we are testing the models in. Secondly, we are creating training materials that can help others use the models and the methodologies in their own geographies. And we are developing a technical report that will really hopefully outline a pathway for achieving global scale seagrass monitoring. This is our roadmap for how we take the results from this project and use them in the future for sustained monitoring of seagrass ecosystems. The project is comprised of several different teams. One is our core team, which is largely our Earth Genome, Nature Conservancy, and Florida International University folks. We also have an advisory committee that is comprised of seagrass experts across the policy arena, the market space, and technical mapping space. Those serve in an advisory capacity and really help us shape the process as well as the deliverables so that the deliverables are most useful across a range of potential use cases down the road. We also have our implementation teams. As mentioned previously, we are piloting these models in 4 target geographies. And these implementation teams are 1 to 3 seagrass experts in each of those focal geographies. They serve as a liaison between the work that the core team is doing and the geographies themselves. They help provide and collate data that can be used for model training and validation. They also help collect additional data. They are also working very closely with the core team to co-develop and fine-tune some of the models to make them particularly useful for those geographies. And ultimately, all of us are working together to create that mapping methodology that can be taken up by others in other geographies, the results and tools that help communicate the outputs, and that training and roadmap. The target geographies were really selected by identifying those varied biophysical conditions, so turbidity, wave energy, etc., to help us understand and explore the different challenges that we might face when trying to test these models and apply these models. We also looked at existing seagrass mapping efforts and data availability. By kind of understanding that space, it helped us identify areas that would really give us a range of both ease and challenge in applying this mapping methodology. Because as part of this project, we really want to test the limits of these foundation models and the modeling approaches. And so we want to be able to test them in varied geographies. We also explored different enabling conditions in the geographies, examples like does the geography have coastal ecosystems included in their nationally determined contributions that might, facilitate seagrass conservation? We also identified potential risks in these geographies, like are there particularly high loss rates in these areas, to identify the potential need and value of the mapping work that we're going to be doing as part of this project. And as such, we identified the U.S. East Coast, the Caribbean, the Mediterranean, and Indonesia as our 4 first pilot geographies. And so, again, just to reiterate, this project is focused on that co-development, the seagrass mapping methodology, the results and the tools for communicating the maps and the models and the approaches, and that training and roadmap for uptake and future sustained use of the mapping methodology and approaches. And I will now hand it over to Ben to talk and to dig in a little bit deeper into the foundation model work.
Thanks, Lindsay. Yeah, now is a really exciting time to be sharing some of the initial preliminary results with this group. I'm glad that we have this chance to share the work that we're already getting to. I just want to share that up front that this is a very much a work in progress. So thanks for um, letting me share that work in progress. And I hope you're excited about the direction that we're headed, because I think this really, like Lindsay set the table in her part of the presentation, shared like this is supposed to be a very scalable approach that we want to make sure is useful to the community as a whole. So um, the before I get into it too, I guess I should also share a little bit. My name is Ben Strong. I represent the Earth Genome, as Lindsay mentioned. Earth Genome, I think a lot of you probably are not familiar with us as an organization, but just real quickly, we are a relatively small nonprofit that's focused on the intersection of technology and data with the environment and conservation work. So we were we were initially really excited about this project because it seems like it's the perfect time to be working on a thing like this. The technology has advanced in remote sensing and AI foundation models for remote sensing such that we have a chance to build something like this, a truly scalable system that can be locally fine-tuned in order to create actionable maps for the first time in a new innovative way that we're hoping is going to provide a lot of value. So with that, let me jump into a little bit about our approach first and basics of AI foundation models. And then I'll share some of the preliminary results that we've been getting from the approach. I think that it's fair to say that everybody here has probably heard of AI foundation models already. I think that it's useful though to clarify exactly how they work and how we're using them for the remote sensing context and the seagrass mapping problem. Foundation models, generally speaking in AI, are large models that are useful for multiple different tasks, and they're pre-trained and by self-studying some large corpus of unlabeled data. That's really the key part that differentiates foundation models from traditional machine learning. Here you can see the schematic side by side of the two approaches. The real key difference is in the foundation model approach, you have that first step, where before you go to the supervised learning stage, where you're actually saying, this is some training data for seagrass, let's learn how to map it. There is a large self-supervised pre-training step where you can just feed a foundation model a bunch of unlabeled data and it can self-study in a way in order to understand patterns in the data. That makes it a lot faster. That's the goal anyway, to make it a lot more efficient in order to move to that second step, that supervised fine-tuning stage. By doing the self-supervised pre-training stage, the model will learn general patterns in the data that allow it to more quickly learn the specific patterns in the label training set that we're using for that supervised fine-tuning stage. So to make that a little bit clearer, next slide, please, Lindsay. This is the basic idea for both text AI foundation models, which you all, I'm sure, are familiar with through things like ChatGPT, and then remote sensing foundation models. For text foundation models, it's really easy to understand that self-supervised pre-training step. You feed a model a whole corpus of text, and it learns to predict from a given set of words what the next word is going to be. That's the way that AI foundation models were able to progress really rapidly, given there's so much training data out there that is unlabeled, but the model can learn from it in this self-supervised sense. Remote sensing foundation models work in an analogous way. There are multiple different ways to train them. I won't go into all the different specifics here, but this is a very common way, as shown in that graphic on the right. Sorry, the citation fell off with that, but that's from a paper called Scale MAE by Reed et al. This is a method here that's called a masked autoencoder. So you have an input image in that left column. It is then masked. We're actually dropping parts of the image out, as you can see in that second column. And then the model learns to reproduce that image in order to be able to learn those general patterns in the data. In this particular model, you see there's a low frequency component it learns and a high frequency component. Really just focus on that right column though, the reconstruction. So the model here is learning from that, being only fed in that mask, the partially obliterated image, how to reproduce that input image as the target. And as you can see, from a pretty severely masked image, the models are able to reproduce what's in the original input image. And that's just a sign that these models are learning general patterns about what's happening in the imagery, which is that foundation of knowledge that then we can take in order to be able to build new models that are fine-tuned for a specific problem like seagrass mapping. Next slide, please, Lindsay. So the advantages of foundation models are here. Really, they come down to three things. Data. Fine-tuning requires less training data than building a model from scratch. Imagery. You can actually incorporate multiple different kinds of imagery into a remote sensing foundation model. Increasingly, foundation models are trained across multiple different kinds of sensors. And all that fine-tuning work, sorry, all that pre-training work makes it easy to fine tune to new AOIs. Not only do you have that reduction in the amount of fine tuning labeled data that's required, but because the models are engineered with this idea in advance that you're going to be using them for downstream applications in this fine tuning context, they're relatively easy to deploy and you're able to build infrastructure around them such that it's easy to adapt in new contexts. So it's not pulling a research code and trying to make it work in a new setting. This is actually something that's well engineered in a way that makes it easier to use in a new setting. And so for all those reasons, we're really excited about foundation models. How to use them in practice comes down to really two different approaches that are most common. One is full fine tuning, so actually taking a labeled data set and fine tuning all the model weights in order to produce something that you want. This is a large neural network, so you're tuning neural network weights. That's one approach it's quite common. The second approach is the embeddings-oriented approach, and that's the approach that we're taking with this project. The difference there is that instead of fine-tuning the complete model, what you actually do is you take the foundation model itself, you remove the last few layers of that neural network, and you treat the foundation model as an encoder. You feed in imagery, the model processes that imagery, and as that last layer that you extract the outputs from, you use that as what's called an embedding vector. And that's just essentially a compressed representation of the input imagery that's fed into the model. That is a compressed representation that's a lot easier to use because it is, instead of a multi-band raw satellite imagery input, it's highly compressed and it has the essential information distilled into a simple embedding vector, which makes it really easy to build tabular machine learning models on top of that compressed representation to do the kinds of things that you want to do. So that's the modeling approach that we're taking. That step one is creating those embeddings. Step two is building a supervised machine learning on top of the embeddings. Next slide, please. Embeddings are already pretty well, or the embeddings are having a moment right now in the remote sensing space. There are a few different projects out there that are making heavy use of embeddings. If you are interested in this topic, I encourage you to check them out. Earth Index is one of them. That's actually a project that Earth Genome works on, my organization. That's building a tool around embeddings in order to make it really easy to search the planet and build basic maps of things. So here you see Earth Index locating solar facilities, and I think that's Cambodia. Alpha Earth is another example of an embeddings-oriented product that Google has produced. You might have seen some news about it last year, I think, when it came out. That's a global embedding set that's available anywhere on the planet, which makes it really easy to pull those embedding features and then make quick use of them in your downstream workflows through Google Earth Engine or through whatever kind of other pipelines you want to generate. And just to share ahead of time before we get there, but Alpha Earth is one of the models that we are using in the Seagrass Mapping project. Next slide, please. I wanted to stress that foundation models are not a panacea. They don't solve every problem. In particular, they just can't get around some of the fundamental limitations that we face in the really difficult problem of seagrass mapping. If you can't make out the seagrass in imagery, the foundation model will not be able to find it for you. That's basically the summary. They can't defy physics, so can't get around these fundamental limitations like turbidity and attenuation. And they can't negate the need to do a really careful pre-processing of imagery. So there still are some of these important considerations when you're working with foundation models. Which makes it so it's really, I think, important to think about the right way to bring a foundation model into a pipeline that's going to be truly scalable. How do we actually make something that's really useful, that's the right degree of customizable for a particular AOI or particular region? And that's been our fundamental challenge as we've been working on this project so far. But so there are these limitations around foundation models, but because of those reasons that I already stated about being able to quickly fine tune for new locations relatively accurately, we're really excited to explore their approach. And that's why we developed a mapping approach that's on the next slide. Thanks, Lindsey. So the goal is to create a methodology that uses different foundation models where we can swap in foundation models relatively easily, anticipating, as I believe, that the future of remote sensing is going to be increasingly powered by foundation models, and those foundation models are only going to improve. So creating a methodology that allows for relatively easy adoption of new foundation models as they're developed, compare those against baseline approaches to really understand, are we improving based off of traditional approaches? And because we care about scalability, we're starting with Sentinel-2 imagery, which is globally available. So that is the quick explanation of the mapping approach. Ultimately, I want to stress too that what we most care about is creating maps that are going to be used rather than the specific approach. So we're really just trying to figure out what makes the best high quality seagrass map that's going to be scalable. Thanks, Lindsey. Next slide, please. To get into some of the specifics of the work we've done so far, we've had um, a real nice opportunity to work with the different implementation teams that are part of this project to collect what I think is one of the coolest data sets out there for seagrass mapping work. Pulling together partner data sets, they're up to around 70 different data sets shared across our 4 regions. And as many of you, I'm sure, appreciate, one of the really most important steps here is making sure that those data sets are standardized, that we can actually use them in a consistent approach. So we spent a lot of work on that, that we are that's important in order to make sure that we have the model drawing consistently from those data sets and that we have the right data sets shared into them. But the data sets do vary in terms of the original kind of uh, input methodology, but ultimately they need to have some consistent things like geolocation, class, and density in order for us to be able to model seagrass extent and understand if we're doing those things correctly. Harmonization work is, like I said, a big part of what we're trying to do in order to make this data set consistent in a way that is appropriate for our model uses. So we've spent a good amount of time trying to figure out how do we take all these different input data sources and make them generally um, standardized for that approach. I I think we could have a whole nother discussion about that harmonization process. Honestly, it's been a really interesting process, and I think I won't go into it here, but that is one of the things that I think we're really proud about is being able to harmonize all these different data sets, and we plan to share that harmonization workflow as well as the data set as this project continues. So I hope that we see that as a core deliverable in the sense of that that's going to be something really useful to the community as well in order to bring together those different data sets in order for anybody to build on them with a consistent approach. Next slide, please, Lindsey. So now I'll share just a few different of the results, a quick summary of the results from our initial um, prototyping of this approach, bringing together those data sets that we've been harmonizing, bringing together that methodology that I walked through a little bit earlier. These experiments are in just limited geographies in order for us to just quickly run out the experiment. Does this methodology make sense? Are we onto something? So we picked relatively straightforward locations to do that first work, just to understand, is this something that's going to be ultimately, like, what do we want to scale? The so the goals were to simply just reproduce something where we already had high quality data. Just use that as a benchmark. How can we reproduce something that was originally produced with a higher resolution map with higher resolution imagery with Sentinel-2 imagery? And answer that question: do foundation models contain the right information in order to do the mapping work we want? And then with that follow-on question of what is what are the limitations around generalizing? How does this actually work in the towards our ultimate goal of scaling and expanding out this work spatially. So we have worked on I guess I'll share just a couple of those quick results, both in Jamaica and the Baleares. So for these prototyping experiments, we recoded the harmonized data set to three different classes: dense seagrass, sparse seagrass, and non-seagrass. We did random sampling of negatives in Jamaica, and we already had some negatives present in the data set in Baleares. So those were how we constructed the data sets. Next slide, please, Lindsay. What we used in order to create the baseline model that we compared our foundation model approaches against was a traditional machine learning approach that relied on 20th percentile Sentinel-2 imagery that we collected over these different AOIs. We tested a few different imagery methods and decided this was the one that produced the highest quality, clearest imagery in order to do this work. You can see some of these different features that we pulled into the modeling pipeline as well. We wanted to make sure that we understood some of the different features that might be useful to a model in order to understand where seagrass is present. So we created some of these hand-derived features and fed them into the model, as well as just the raw spectral bands and band ratios. So things like depth, HSV, which is just a colored space transform, and then a measure of texture. This is you'll see, I think, the K3 different kernel sizes for spatial pattern statistics in order to understand just some kind of structural signal in the imagery as well. So just to preview what's on the next slide, yeah, or maybe in a few slides here, we'll have some of these terms come back as features in the different models that we experimented with. Against that baseline approach, we tested the models that we wanted to explore for the foundation model driven approach. Those were Alpha Earth, as I mentioned earlier. You can read some of the details for how that Alpha Earth model was trained and some of the data sets that went into it. You can see really clearly there, it's using multiple sensors, as I mentioned, as one of the advantages of foundation models. And it's pre-trained on Allen Coral Atlas and Murray intertidal data. So those are some data sets that are really relevant for the seagrass mapping problem, which made us excited about that particular foundation model. Alongside Alpha Earth, we tested out some other publicly available foundation models, including Olmo Earth, which is a model that is trained by the Allen Institute for AI, and Tessera, which is a model out of a group at Cambridge. So we tested all three of those models side by side with the baseline approach. Thank you, Lindsay. Next slide. We wanted to make sure that we were doing this work in a robust way that could hold up to scrutiny. It included things like cross-validation, tried different machine learning approaches, and tried to understand a little bit of that spatial generalization problem through a geographic train test split. That's particularly interesting for the results from Baleares, where you can see on the right, we had multiple fold approach where we left one out or left multiple islands out through different training regimes where we trained on multiple islands and then deployed across that held out island, which allowed us to understand a little bit more about the generalizability that we want to make sure that we understand as we move on to the next phase of this project. Okay, thank you, Lindsay. Yeah, here's the slide that I think is really maybe the one that best summarizes the results. The chart here shows results for our different experiments in Jamaica, both foundation model approaches listed there as grouped into AEF as the Alpha Earth Foundation model. Those are the group at the top. Tessera as a second group, which is another foundation model. Olmo is the group at the bottom, the third foundation model approach that we tested. and then no embeddings models at the bottom, which are foundation model free approaches. For each of the different rows, you can see we have different flavors of the foundation model, plus different models that we use in order to train on top of the embeddings that are produced by the foundation model. And that lets us understand what features are most useful for the models and how these different models compare with the kinds of information they're already producing from the imagery that they're ingesting. What's the most important takeaway for me is that the no embeddings approaches, those baseline approaches that we tested, are scoring lower in terms of precision recall in F1 than the foundation model approaches. So that was just the baseline takeaway that we wanted to see, that the foundation model approaches are able to produce something that's a higher scoring model than the baseline approach. So that made us excited to continue with the foundation model approach for the project. And then within those foundation model approaches, the Alpha Earth Foundation model, there you see in the group at the top, was our top performing model. Alpha Earth, Olmo, Tessera, they all score relatively well, but Alpha Earth was the top performing model in Jamaica, and in a second you'll see Baleares results as well. So that is the model that we have chosen to move forward with. Within the Alpha Earth family of models there, you can see we tried multiple different kinds of input features. P20 is shorthand for those 20th percentile imagery features that I mentioned earlier. Texture is the denotes that texture feature that I mentioned earlier, the spectral feature that I mentioned earlier, sorry, the structural feature that I mentioned earlier. And so one other takeaway is that those extra inputs that we hand create, those hand-derived features that we think might be relevant for seagrass mapping, do make a difference for the ultimate model quality as well. That's still something we're experimenting with, exactly what kind of features to input into the model alongside foundation model embeddings. But I think that's one of the things that we're excited about as a potential path for the ultimate methodology that we'll deploy across our different implementation team regions. Next slide, please, Lindsey. This is about Baleares results. This is just confirmation of the previous slide that Alpha Earth performed relatively well in the Baleares example, just as before. So that gave us additional confidence that we were ready to move forward with Alpha Earth as the core model that's going to be powering the mapping work moving forward. Thanks, Lindsey. This is a slide showing that leave one island out validation work that I mentioned earlier in the Baleares of understanding what does it mean to train on one set of islands and deploy on a third or on a one that's held out. You can see here the F1 score, which is a summary statistic that we're using in order to understand the model quality, does have a significant degradation for that leave one out validation work. The dashed bars show that as the leave one out validation. I think that everybody here is probably not surprised by that. We certainly weren't surprised that the model degrades if you train it on one area and you deploy it on another area. That's something that's very common in remote sensing. I think actually I was happy to see that that the Alpha Earth model in particular seemed like it had less degradation in model quality than some of the other approaches that we tested. So I think in that sense, this is something that we want to really pay attention to because it is one of the fundamental challenges of remote sensing workflows is being able to map generally, particularly in areas where you don't have good reference data. But this is something that we feel like the foundation model approach might give us an angle in order to have a little bit more success there, even though it's still going to be a challenge. Thanks, Lindsey. Next slide, please. The takeaways here for model performance, as I mentioned earlier, the Alpha Earth model performs best across both project sites. Our understanding, our belief is that that is likely due to the pre-training on benthic mapping tasks, as I mentioned earlier. Tessera and Olmo also show signal, but they underperform Alpha Earth. I think that's probably because they just did not have a pre-training task that was close to seagrass mapping. Another takeaway is that adding composite and texture features does help generalization and does help model performance, but Alpha Earth alone performs well as well. So there's one of the trade-offs that we're navigating here is this trying to build something that is accurate and as um, high quality as possible in terms of data outputs while still being really something that's easy to deploy. Something we're still navigating a little bit here. Um, and another takeaway is that spectral and texture alone trail all embedding approaches. So that's the baseline approach does not is the baseline we exceed the baseline approach with foundation models, which um, make us excited about continuing with that approach. Thanks, Lindsey. Um, so again, the more takeaways here, Alpha Earth is our current default. I think we're pretty set on moving forward with that. In addition to Alpha Earth being our best performing in terms of model quality, it's also one of the easiest to deploy because Alpha Earth embeddings are already available at 10 meters on Google Earth Engine. Anybody can pull them right now. I encourage you to play around with them if you would like. Uh, the I also want to share that we don't believe that embeddings are the only approach that can work for this problem. We didn't, I didn't share any results about fine-tuning in these slides, but we have been exploring fine-tuning foundation models as well, and that has shown promising results. But because of the simplicity of using embeddings, we are planning to move forward with the embeddings approach as our current approach. We'll see what that looks like in the future, though, as foundation models improve and as fine-tuning becomes simpler. I think we want to make sure we keep our eye on how we expect that future scenario to evolve. And in particular, I'm curious. Maybe a coastal foundation model is an exciting future opportunity for to be developed in order to be able to map not just seagrasses, but all kinds of coastal ecosystems in order to be able to understand how they in order to be able to understand um, their extent and changing over time and different important characteristics of those ecosystems. All right, so next steps, just wanted to share these. We are continuing to do the work around harmonizing the training data set. It's a lot of work to harmonize all those different data sets that we've pulled together. We are extending out next to East Coast and Indonesia and expanding in the AOIs that we've already taken a look. And then doing a little bit of work on exploring this region-specific feature selection in order to improve the model quality and in particular AOIs while still keeping an eye on that. How do we do something that's relatively simple and easy to deploy while creating really the most accurate maps at the same time? Those twin goals, trying to balance those. Thanks, Lindsey. And with that, I guess that's all that I wanted to share. Thanks for everybody paying attention and hope that was interesting. We will be continuing. This project the timeline runs for about another 9 months. So stay tuned for public sharing of project results and the methodology. Really hope that this community is interested in reviewing that and potentially adopting it. That's really the key to our approach. We set out for this project with the goal to um, with the understanding that the only way that we'll succeed is by having partners adopt the methodology. So we're really um, interested in seeing this methodology adopted by the wider community, and thank you for any input or thoughts you have about that. If you have thoughts about data methodology or applications, we'd love to hear them. We have our project website linked there, seagrassblueprint.org. feel free to check it out. We have a form on the website. You can also just email me or Lindsay directly. Happy to share those emails with anybody who would like to reach out. But look forward to hearing from you and look forward to your questions. Thank you.
Thanks, Ben. Thanks, Lindsay. Yeah, we've got time for questions now, if anybody has any. Anybody's got questions? I'll start us off then. Um, I was wondering, so this is for both intertidal and subtidal mapping, isn't it?
Sorry, I lost my mute button.
Yeah, no problem.
We are, um, yeah, I think so. We're trying to expand to as many different kinds of seagrass ecosystems as possible. I think that I guess what we've mapped so far is just subtitle, right, Lindsay? Yeah.
Yes,
Okay.
so far just subtitle. But yeah, we are trying to expand and ensure that we can capture both intertidal and subtitle. But we aren't identifying species level information. It's just seagrass presence or absence.
Hmm. Okay. Okay, yeah, thanks. Because I was just wondering, like, then what is the, I guess, yeah, the quality of the recognition between intertidal and subtidal, but I suppose this is all a work in progress. Thanks.
Stay tuned.
Christina, you've got a question.
Hi, thank you very much for the interesting talk. I'm coming in from Halifax, East Coast, Canada. We do a lot of mapping for our eelgrass up here, mostly using multispec drones. So one question would be how you're using multispectral imagery. I think you touched on it. And the other one, and sorry if I missed it, I'm really curious about the density parameter you mentioned and how you're tackling that because that's making us sweat on our end.
Yes, those are great questions. So multispectral, we are using alpha Earth embeddings, which have as input to them multispectral imagery, not drone imagery, but Sentinel-2 and some other kinds of sensors as well. And that's the approach that we're using. We are not using drone imagery, like I said, which I know is kind of the gold standard for this mapping work. Really, what we're trying to do is something that's scalable. So we're focusing on data sources that are available everywhere. And then density. So we're not directly modeling density. We're just using that as a way to understand our data set and set parameters around what we are ultimately going to be able to map or not. I think there's ultimately going to be a cutoff for density that we're not going to be able to map less than a certain density.
All right, thank you.
Yeah.
Do we have any other questions? Going once, twice.
Can I ask another one?
Of course, go for it.
For the ground truthing, do you use like local data, like really in-water data, or just based on the Sentinel data?
Yeah, that's one of the cool things about working with these implementation teams is that we have in-water data for these different regions. We have to, again, keep an eye on scalability. The in-water data is not available everywhere in these different regions, so we have to have an approach that kind of blends existing maps with in-water data in order to be able to understand, in order to be able to build out in a generalizable way. But yes, definitely have a lot of in-water data. And that's one of the great components of this project that we didn't really hit on is that we're able to provide funding to our implementation teams to go out and collect additional in-water data in order to then help us build models and understand their quality. So there will be a lot of field data that's published as a part of this project as well.
Yeah, and just to follow up on that, we just had a workshop in Jamaica that showcased the different ways that our implementation teams collect in water data and tried to identify the similarities across those different ways of collecting data in hopes and help to kind of generalize and create this harmonized global reference data set that we're creating as part of this project. And I will note that the density piece is a challenging one because density is captured very differently across these different data sets and field data collection efforts. Sometimes it's captured in a more categorical way, sometimes it's captured in a more continuous way. And so harmonizing and standardizing that density classification is one that we are continuing to iterate on. In fact, we're going to have like a virtual workshop on across our implementation teams to get their insights on that density piece.
Thank you. If that is of interest, we are sitting on a ton of density and survey data for Atlantic Canada. So for the last 6 years, happy to discuss if that would be helpful, like retrospect or current, obviously.
Yeah, absolutely. I mean, would love to catch up with you or connect with you after. That would be
Yeah,
great.
I'll put my email in the chat. Thank you.
Perfect. Thank you.
Manuel, you have a question as well?
Hi everyone. Hi Ben. Thank you for the talk. I'm Manuel. I'm working here in Mexico. We work with surf grasses, which grow over rocks. And I wanted to ask you how much of your model depends on a high contrast between the color of the seagrass and the color of the substrate. I'm asking that because here the substrate is always pretty dark. Is composed by rocks and also a lot of brown macroalgae. Have you worked with that type of setup, or how would you deal with that? Thank you.
Yeah, that's an interesting question. So I think that directionally, your intuition, if anything, appears to be harder because of those factors, it's going to be harder for like I said, foundation models cannot solve every problem. And if it's just impossible to make out the difference in imagery for whatever reason, then we are not going to be able to get around all those different issues. But my hope would be that the approach that we're using is able to push a little bit farther out in order to be able to do things that weren't possible by virtue of bringing in multiple different kinds of sensors, the multispectral approach. I've not looked at that particular problem specifically, so I can't comment, I guess, on your particular region of interest. Would love to understand more about that though, and see if we're able to produce something that's relevant. So I'll have to put that on my list for a place for us to check out more specifically in the future. Um, but yeah, I guess I don't really know. I think that I hope that we're able to say something, but it wouldn't surprise me if that's still a really hard modeling challenge.
Thank you very much.
Yeah, you're welcome.
Right. Any final questions from anybody before we let you all go? Nope, doesn't seem like it. Okay, so Ben and Lindsay, you have shared your emails in the chat if anybody needs to reach you. I have also shared the YouTube channel where you can catch all the past webinars and this one after this. Once again, everyone, let's thank Ben and Lindsay for sharing their work. And thank you all for attending this webinar. Hope to see you again in the future. Thank you.
Okay.